the delicate sapphire glaze of a high-end porcelain vase, or the deep ink blue tint of a luxury perfume bottle represents one of the most sophisticated chemical deceptions in the modern household. To the casual observer, these objects radiate a sense of serene, frozen beauty, a color so stable it appears to have been plucked directly from the deep ocean or the midnight sky. Yet this visual tranquility is provided by the 27th element of the periodic table, a material that simultaneously serves as the high-stakes, volatile engine of the digital revolution. While one facet of this metal is used to enchant the eye on a dinner table, another version of the same substance is likely resting in the pocket of that very same observer, hidden within the pressurized, energy-dense layers of a smartphone battery. This is cobalt, an element that functions as the shadow cardinal of our technological era, silently governing the lifespan of our electronics and the safety of our transportation, while carrying a historical legacy of fear, superstition, and artisanal obsession. As the hidden architecture of our modern tools is unraveled, subscribing to this resource and sharing a perspective in the comments ensures that the intricate narratives of the materials shaping our reality continue to reach a wider audience of curious minds. The physical paradox of cobalt begins with its remarkable ability to manipulate the behavior of light. To understand why a microscopic amount of this metal turns clear glass into a vibrant blue, one must examine the specific electronic configuration of the cobalt atom. In its ionic state, cobalt possesses a set of d orbitals that are not completely filled with electrons. When these atoms are introduced into a molten silicate matrix, the basic substance of glass, they do not merely mix, they become an integral part of the molecular geometry. These unsettled electrons absorb very specific wavelengths of light, particularly those in the red and yellow portions of the spectrum. To explain this on the fingers, cobalt acts like a highly selective gatekeeper in a crowded hallway. It allows the blue energy of the light to pass through or bounce back to the eye, while it captures and swallows all the other colors. This process is so efficient that even a concentration of 1 part per thousand is enough to saturate a material with a color that will not fade, oxidize, or degrade, even if exposed to direct sunlight for 10 centuries. This is why the blue found in ancient Egyptian artifacts or Ming Dynasty porcelain remains as vivid today as the day it emerged from the kiln. The cobalt atoms are physically locked into a mineral cage that time itself cannot erode. However, the modern importance of cobalt has shifted from the surface of the object to the internal mechanics of energy storage. If one were to surgically dismantle a contemporary lithium-ion battery, they would find that the most critical component is the cathode, the positive electrode that dictates how much power the device can hold and how many times it can be recharged before it becomes a useless slab of plastic and silicon. In the most advanced versions of these batteries, the cathode is composed of a complex crystal lattice known as lithium cobalt oxide, LiCOO2. To understand the engineering necessity of cobalt in this context, one can visualize the interior of the battery as a massive, multi-story warehouse designed to store lithium ions. These ions are the goods that move back and forth as the battery charges and discharges, a process engineers call intercalation. The primary challenge in battery design is maintaining the structural integrity of this warehouse. When a smartphone is plugged into a wall outlet, the electrical current physically pulls the lithium ions out of the cathode structure and pushes them into the anode. This is comparable to removing all the support pillars from a building simultaneously. In a battery that lacks cobalt, the remaining layers of the cathode would lose their balance and collapse into a dense, disorganized heap. Once this collapse occurs, the warehouse is ruined. The lithium ions can no longer find their way back in, and the battery's capacity drops to zero. Cobalt atoms serve as the permanent, unyielding rebar of this atomic structure. Because they possess a high degree of structural stability and do not move during the charging process, they hold the crystalline layers apart, creating wide open galleries for the lithium ions to return to. This mechanical resolve is the reason why a modern smartphone can be recharged over 1,000 times without the battery physically disintegrating from the inside out. The role of cobalt as a stabilizer extends into the realm of thermal management and safety. The energy density of a modern battery is a double-edged sword. We demand that a massive amount of electrical potential be packed into a space thinner than a pencil. This creates a state of extreme chemical tension.
If the internal temperature of a battery rises too quickly, due to a fast charge or a microscopic short circuit, the material can enter a state of thermal runaway. This is a catastrophic causal chain where the heat triggers the release of oxygen from the cathode, which in turn fuels a fire that cannot be easily extinguished because it provides its own oxidizer. Cobalt is uniquely effective at resisting this breakdown. Its atomic bonds are so robust that it requires a much higher temperature to force the oxygen to leave the lattice compared to cheaper alternatives like manganese or iron. Cobalt is the cool-headed regulator in a high-stress environment, ensuring that the chemical frenzy of the battery remains contained and predictable. This leads to the socio-economic paradox of the element. Cobalt is a strategic bottleneck metal. Despite being the sibling of iron and nickel, it is found in much smaller quantities and is significantly harder to isolate. While iron forms entire mountain ranges, cobalt is a perpetual hitchhiker, appearing only as a trace impurity in the ores of copper and nickel. This means that to satisfy the world's hunger for electric vehicle batteries, industrial mining must process millions of tons of host rock to retrieve a relatively small amount of the blue metal. This scarcity has elevated cobalt to the status of white oil, or the blood of the Green Revolution. The global economy is currently tethered to the availability of this specific atom. Without it, the transition from fossil fuels to portable electricity would be slowed by decades, as no other element provides the same combination of structural strength and energy density. The shadow nature of cobalt is further reflected in its industrial anonymity. Unlike gold, which is paraded on the skin, or aluminum, which forms the visible shell of an aircraft, cobalt is almost always hidden. It is the invisible coating on a drill bit that allows it to cut through hardened steel without melting. It is the secret ingredient in the superalloys of a jet engine that prevents the turbine blades from stretching and snapping at 2000 degrees Fahrenheit. We live in a world that is propped up by cobalt, yet we only encounter it as a color or a percentage on a specification sheet. It is an element that performs the heavy lifting of modern civilization, while remaining shrouded in the aesthetics of luxury or the casing of a battery. To look at a blue-tinted glass bottle or the glowing screen of a phone is to witness the two faces of the 27th element. On one side, it is the master of optics, using its electrons to tune the spectrum of light and provide a sense of timeless elegance. On the other, it is the master of structural engineering, using those same electrons to hold the atomic walls of our energy future in place. Cobalt is the element that bridges the gap between the ancient craftsman and the modern battery engineer. It is a material that demands absolute precision in its handling, as its reactive potential is as great as its structural resolve. This blue demon of the medieval mines has been successfully drafted into the service of human progress, proving that the most difficult and temperamental substances in nature are often the ones that provide the essential framework for our most advanced aspirations. We have taken a mineral that was once synonymous with curses and transformed it into the silent, silver-blue pulse of the 21st century, a material that ensures our world remains both beautiful to look at and powerful enough to move. The presence of the 27th element within the accessible layers of the Earth is a consequence of a profound cosmic scarcity, marking a narrative where the standard output of the universe's most powerful engines
resulted in a material that is as rare as it is essential. To comprehend the origin of a single cobalt atom, one must look past the steady, rhythmic fusion that powers a medium-sized star like the Sun, and into the terminal, frantic spasms of celestial giants. While common structural elements such as oxygen, silicon, and iron are produced in gargantuan quantities during the stable life of a star, cobalt occupies a position of extreme thermodynamic difficulty. In the grand inventory of the cosmos, cobalt is nearly 1,000 times less abundant than iron, despite being its immediate neighbor on the periodic table.
This disparity is not a matter of chance, but is a rigid outcome of the iron peak in nuclear physics, a point where the stellar furnace reaches a state of energetic bankruptcy. To explain the mechanism of this cosmic bottleneck on the fingers, a star functions as a high-stakes energy business. For millions of years, it generates a profit by fusing light elements like hydrogen into helium, releasing the outward pressure that keeps the star from collapsing under its own gravity. As the star exhausts its fuel, it begins to cook heavier and heavier elements: carbon, neon, magnesium, and eventually silicon. Each step yields a smaller energy return, but the business remains solvent. However, when the star reaches the stage of producing iron, 26 protons, cobalt, 27 protons, and nickel, 28 protons, it hits a metaphorical brick wall. Iron 56 is the most stable nucleus in existence. To fuse elements beyond this point does not release energy, but instead consumes it. For a star, producing cobalt is a loss-making enterprise. The moment a massive star begins to forge these heavy metals in its core, the outward pressure vanishes, and gravity, winning the struggle, causes the entire structure to implode in a fraction of a second. The cobalt that eventually reached our planet was forged during the violent rebound of this collapse, the supernova. In those final apocalyptic seconds, where temperatures exceed 3 billion degrees Fahrenheit, the environment is flooded with a concentrated hurricane of free neutrons. This is known as the R process, or rapid neutron capture. Iron nuclei act as seeds that are bombarded by these neutrons at such a rapid frequency that they transform into heavier elements before they have a chance to decay. Cobalt is one of the specialized byproducts of this high-energy chaos, a fragment of stellar shrapnel ejected into the interstellar void at speeds approaching 20,000 miles per second. This material drifted through the vacuum for eons as microscopic dust, eventually becoming part of the cold molecular cloud that would collapse to form our solar system approximately 4.6 billion years ago. The arrival of cobalt on the infant Earth was governed by a secondary filter, the process of planetary differentiation, often referred to as the iron catastrophe. During the first few million years of the Earth's existence, the planet was a roiling sphere of liquid fire, heated by radioactive decay and constant celestial impacts. In this fluid state, gravity performed a planetary-scale sorting of matter based on its specific weight and chemical affinity. Cobalt is classified by geochemists as a siderophilic or iron-loving element. Because its atomic structure allows it to dissolve easily into molten metal, the vast majority of the Earth's primordial cobalt followed the iron and nickel as they sank toward the center to form the core. To explain this on the fingers, it is as if the Earth acted as a massive centrifuge, pulling all the precious heavy metals 1,800 miles beneath the surface. It is estimated that enough cobalt resides in the Earth's core to cover the entire surface of the planet in a layer several meters thick. However, this treasure is locked away under pressures exceeding 3 million atmospheres, rendering it permanently inaccessible to human technology. If the history of the Earth's formation had concluded with this sorting, there would be no cobalt to power a smartphone or glaze a porcelain vase. The surface world would have been an elemental desert, stripped of the metals necessary for high-tech evolution.
The existence of mineable cobalt in the crust today is the result of a cosmic refill and a specific geological hitchhiking strategy.
Much of the cobalt we use arrived later, during the late heavy bombardment, when a rain of asteroids and meteorites salted the already cooling crust with a fresh supply of heavy elements. Furthermore, the cobalt that remained in the mantle did not form its own independent deposits. Cobalt is the ultimate elemental introvert. It does not like to be alone and lacks the chemical drive to form massive self-contained mineral veins like iron or copper. Instead, it exists as a shadow element, hiding within the crystalline structures of other metals. To understand the engineering of this concealment, one must look at the atomic radius of the elements. Cobalt ions are nearly identical in size to nickel and copper ions. Because of this geometric symmetry, cobalt atoms are often mistakenly incorporated into the lattice of nickel-bearing minerals like pentlandite or copper-rich ores. In the language of mineralogy, cobalt is a perpetual stowaway. It waits for millions of years, trapped as a minor impurity, often representing less than 0.1% of the total rock mass, within the massive geological formations of the Earth's crust. The concentration of this stowaway into a strategic resource is a process of extreme geological patience, involving the movement of superheated H2O and the slow grinding of tectonic plates. In specific regions, such as the Central African Copper Belt or the nickel laterites of Australia and Canada, hydrothermal fluids circulating through the crust at pressures high enough to fracture solid rock have, quote, 28, quote, these trace cobalt atoms and redeposited them in more concentrated zones. This is a form of natural chemical distillation, where the Earth uses its internal heat to gather the, quote, 29, quote, from 1,000 square miles of mantle and focus it into a single, accessible ore body. The most significant concentration of this element occurred in the sediment-hosted deposits of the Democratic Republic of the Congo. Hundreds of millions of years ago, this region was a vast, shallow sea. As organic matter settled and salt levels fluctuated, the chemical environment became a, quote, _30_ for the cobalt and copper ions carried by ancient river systems. The cobalt did not just settle, it was chemically, quote, 31 to the sediments, creating the world's largest and most high-grade reservoir of the 27th element. Today, this single point on the map accounts for over 70% of the global cobalt supply, creating a geopolitical bottleneck that tethers the entire digital economy to a specific patch of African soil. Another, more exotic source of cobalt is found at the bottom of the abyssal plains, the polymetallic nodules. Over millions of years, trace amounts of cobalt dissolved in seawater have precipitated around tiny fragments of bone or rock, forming potato-sized lumps rich in manganese, nickel, and cobalt. This is a process of __quote_32__ performed by the ocean itself, at a rate of only a few millimeters every million years. These nodules represent a massive untouched warehouse of the element, a literal carpet of __quote_33___ waiting in the permanent darkness of the deep sea. The cosmic accident of cobalt is thus a story of double rarity. It is an element that the universe found difficult to manufacture, and which the Earth found difficult to keep on its surface. Every gram of cobalt used to stabilize a modern battery or pigment, a luxury artifact, is a survivor of a kilonova collision, a hitchhiker that escaped the gravitational pull of the Earth's core, and a chemical prisoner that had to be liberated from the shadow of more common metals. We are utilizing a material that sits at the absolute limit of what the laws of nuclear physics allow a star to produce before it dies. Cobalt is the heavy ghost of the periodic table,
a material that moved from the frantic energy of a collapsing giant to the silent depths of the saline ocean and the copper-rich soils of the Rift Valley. This cosmic heritage ensures that cobalt remains one of the most strategically sensitive materials in our inventory. It is the noble scarcity that allows us to manage energy at the scale of the atom, provided we can find where the Earth has hidden its tiny, precious supply of stellar ash. To look at a cobalt deposit is to see the reject pile of a supernova, the trace remains that were never meant to be common, yet became the indispensable foundation for a civilization that refuses to slow down.
The history of the 27th element is not merely a record of metallurgical progress, but a long-form narrative of human terror, linguistic evolution, and the eventual realization that the Earth's most frustrating impurities are often its most valuable assets. For centuries, the story of cobalt was written in the darkness of the medieval silver mines located in the Erzgebirge mountains, a jagged range dividing Saxony and Bohemia. To understand the cultural and industrial weight of this metal, one must look past the modern laboratory and into the sensory reality of a 15th century miner. These individuals labored in an environment of absolute darkness and constant physical peril, driven by a single economic imperative: the extraction of silver. In this geological environment, silver was the primary currency of power, and any material that interfered with its recovery was viewed not as a scientific anomaly, but as a deliberate act of supernatural sabotage.
The historical drama began with the appearance of a specific type of ore that possessed a deceptive silver-white luster. To the eyes of a medieval miner, this material appeared identical to the high-grade silver they sought, promising wealth and social elevation. However, when this ore was brought to the surface and subjected to the intense heat of a smelting furnace, the expected yield of liquid silver never materialized. Instead of melting into a precious pool of metal, the ore proved to be entirely intractable, remaining solid or turning into a gray, brittle slag that fouled the equipment. Even more disturbing was the chemical byproduct of this failed transition. As the furnace temperature climbed toward 1,500 degrees Fahrenheit, the ore released a cloud of invisible, garlic-smelling vapor that proved to be lethal to the workers. To explain this on the fingers, the miners were attempting to bake a loaf of bread using a stone that looked like flour but behaved like a poison. In the pre-scientific world of the Middle Ages, where the laws of chemistry were obscured by myth, this industrial failure was attributed to the kobold. In Germanic folklore, the kobold was a malicious subterranean spirit, a mountain gnome believed to dwell in the cracks of the rock. The miners became convinced that these spirits were stealing the true silver and replacing it with a cursed, worthless substance that mimicked the appearance of wealth but carried the sting of death. The word cobalt is the direct linguistic descendant of this demon, a permanent record of the era when the element was seen as the physical manifestation of a spiritual grudge. The poisonous breath of the kobold was actually a consequence of the metal's geological associations. In the Earth's crust, cobalt is frequently found bonded with arsenic and sulfur. When heated in an open furnace, these compounds undergo a rapid oxidation, releasing arsenic trioxide and sulfur dioxide into the atmosphere. The miners were not being cursed by gnomes, but were being systematically poisoned by the thermal release of one of the most toxic elements in nature, all because they were trying to force a, quote, 41 to behave like silver. For nearly 3 centuries, cobalt remained a pariah of the mining industry, a material to be avoided or discarded as hazardous waste. The transition from a cursed stone to a global commodity required a fundamental shift in perception, moving from the pursuit of mass to the pursuit of color. Long before the metal was isolated in its pure form, artisans had discovered that the quote, _42 from these silver mines possessed a singular, transformative property. When roasted and mixed with molten glass, It produced a blue of such depth and intensity that it had no rival in the natural world. This was the birth of quote, 43 a concentrated blue glass that could be ground into a fine powder and used as a pigment. To explain the engineering of this pigment on the fingers, the cobalt atoms within the roasted ore function as highly specific light absorbers. When integrated into a silicate lattice, the cobalt ions interact with the incoming spectrum of white light. Because of the specific energy gaps in the cobalt atom's electron shells, the material swallows the red and yellow wavelengths of light, allowing only the high-energy blue photons to escape and reach the observer's eye. This was an early form of molecular tailoring. The resulting color was not a surface coating, but a structural property of the material, which meant it was immune to the fading effects of ultraviolet radiation or the corrosive influence of moisture. This quote 44 had inadvertently provided the most durable and vibrant pigment in human history, turning the quote 45 of the silver mines into the most sought-after additive for the glassmakers of Venice and the potters of the Low Countries. The formal scientific redemption of cobalt occurred in 1735, orchestrated by the Swedish chemist Georg Brandt. In an era when the scientific community believed there were only 6 or 7 metals in existence, Brandt set out to prove that the blue pigment derived from the quote 46 ore was not the result of bismuth or iron, but was a unique element of its own. To achieve this, he utilized a process of extreme reduction that anticipated the high-energy chemistry of the industrial age. Brandt took the roasted cobalt ore and subjected it to a sequence of acid baths and high-temperature charcoal smelting. By carefully managing the oxygen levels within his crucibles, he managed to strip away the arsenic and the sulfur, leaving behind a small, solid bead of a new metal. The physical reality of the material Brandt revealed was a silver-grey metal with a slight reddish tint, possessing a hardness and a melting point of 2,723 degrees Fahrenheit, which is significantly higher than that of copper or gold. Brandt named the element cobalt, choosing to reclaim the miner's term of derision and turn it into a title of scientific achievement. He had successfully demonstrated that the worthless stone of the medieval mines was actually a semi-metal of extraordinary stability. This isolation was a watershed moment for modern chemistry. It was the first time a metal had been discovered that was not known to the ancient world, effectively breaking the conceptual limit on the number of building blocks that could constitute the physical universe. The historical drama then shifted from the laboratory to the trade routes of the global empire, as cobalt blue became the defining aesthetic of the Ming dynasty in China and the luxury markets of Europe. To produce the iconic blue and white porcelain that defines an entire era of human culture, Chinese artisans required a source of cobalt that could withstand the extreme temperatures of a porcelain kiln, which often reached 2,300 degrees Fahrenheit. Many other pigments would simply vaporize or turn brown at these temperatures, but the cobalt-silicate bond is so thermodynamically stable that the color remained crisp and vibrant. Because domestic Chinese sources of cobalt were often rich in manganese, which resulted in a duller, grey-blue hue, the empire established a massive logistical chain to import Mohammedan blue, a high-purity cobalt ore from Persia. This created a global color economy where a rare metallic impurity was traded across thousands of miles of the Silk Road, linking the mineralogy of the Middle East to the artistic mastery of the Far East. In Europe, the monopoly on cobalt production became a matter of state security and economic dominance. In the 18th and 19th centuries, the blue works of Saxony were among the most secretive and profitable industrial sites on the continent. The process of making smalt was guarded with the same intensity that a modern nation might guard its semiconductor manufacturing secrets. The blue powder produced from these factories was exported to every corner of the globe, used to whiten linens, dye paper, and decorate the glassware of royalty.
The element had completed its transformation. It was no longer the demon that stole silver, but the blue gold that generated it. The transition from art to high-stakes industrial engineering occurred in the early 20th century as the world moved into the era of internal combustion and global warfare. Engineers realized that the same atomic stability that kept the blue in porcelain also made cobalt an ideal component for superalloys. By mixing cobalt with chromium and tungsten, metallurgists created stellite, a material so hard that it could cut through other steels as if they were wood, and so heat-resistant that it could function inside the red-hot cylinders of an early aircraft engine. This was the moment the kobold returned to its metallurgical roots, no longer as a nuisance, but as the essential stabilizer for a civilization that was beginning to demand extreme performance from its machines. To look at the history of cobalt is to observe the slow, methodical taming of a subterranean rebel. We moved from fearing its fumes and cursing its presence to utilizing its electrons to manipulate the very spectrum of light. We built an entire global trade network around its color and an entire industrial infrastructure around its hardness. The historical drama of cobalt is the story of how humanity learned to look past the immediate value of a material, its weight and its luster, and instead understand its deeper atomic characteristics. Every sapphire blue stained glass window in a cathedral, and every piece of fine china is a physical record of the moment we stopped seeing the kobold as an enemy and began to see it as an architect of beauty and strength. The 27th element remains a material of profound contradictions, a metal born in a supernova, mistaken for silver, feared as a demon, and eventually elevated to the status of a strategic necessity. It is the silver-blue thread that connects the superstitions of the Dark Ages to the high-definition, high-energy reality of the present, proving that in the world of the elements, there is no such thing as waste. There is only matter waiting for the right level of heat and the right degree of human curiosity. The operational stability of the contemporary high-technology landscape is maintained by a hidden reliance on the specific atomic architecture of cobalt, an element that has transitioned from the visible glazes of ancient art to the invisible nervous system and skeletal structure of modern electronics and aerospace engineering. While the public perception of cobalt is often tethered to its historic role as a pigment, its true industrial weight in the 21st century is localized within the most energy-dense and thermally aggressive environments ever engineered by the human species. Cobalt functions as the ultimate structural stabilizer, providing a combination of mechanical resolve and chemical indifference that allows for the extreme miniaturization of portable power and the sustained operation of jet propulsion at temperatures that would cause conventional metals to flow like warm wax. To comprehend the hidden engine of the present era is to examine how the 27th element manages the flow of ions in a battery and the stress of centrifugal forces in a turbine with a precision that dictates the limits of global mobility. The most critical and pervasive application of cobalt occurs within the cathode of the lithium-ion battery, a component that serves as the primary reservoir for energy in nearly every smartphone, laptop, and electric vehicle in existence. To understand the engineering necessity of cobalt in this context, one must analyze the process of intercalation, the movement of lithium ions into and out of a solid crystalline lattice. A modern battery operates on the principle of a chemical rocking chair. When a device is charging, lithium ions are physically forced out of the positive cathode and pushed into the negative anode. When the device is in use, the process reverses and the ions flow back to the cathode. This movement is not merely a passage of particles through a vacuum, it is a violent structural event.
As the lithium ions exit and enter the cathode, the material undergoes a repetitive cycle of mechanical expansion and contraction, similar to a lung breathing or a sponge being squeezed and released thousands of times. The primary engineering challenge of this cycle is the prevention of structural collapse. In a battery that lacks a robust stabilizer, the removal of lithium ions during the charging phase is equivalent to removing the support columns from a multi-story building. Without these pillars, the atomic layers of the cathode would lose their geometric alignment and settle into a dense, disorganized heap. Once this structural failure occurs, the parking spaces for the lithium ions are permanently erased, and the battery loses its capacity to hold a charge. Cobalt is the material that prevents this terminal decay. Within the crystal lattice of a lithium cobalt oxide cathode, the cobalt atoms occupy fixed, unmoving positions. They act as the permanent rebar of the atomic structure, holding the layers apart and maintaining the open galleries through which the lithium ions can travel. This mechanical discipline is the reason why a flagship smartphone can survive 3 years of daily use without the battery physically disintegrating from the inside out. The presence of cobalt also dictates the safety and energy density of the device. Cobalt-based cathodes allow for the packing of more energy into a smaller physical volume than almost any other chemistry, a metric known as specific energy. This is what transformed the electric vehicle from a slow-moving curiosity into a high-performance machine capable of accelerating from 0 to 60 miles per hour in less than 3 seconds. However, this density creates a high-stakes thermodynamic environment. If a battery is charged too rapidly or suffers a microscopic internal short circuit, it can enter a state of thermal runaway. This is a causal chain of destruction, where the internal heat triggers the release of oxygen from the cathode material, which then fuels an intense, self-sustaining chemical fire. Cobalt's atomic bonds are remarkably resilient to thermal agitation. They hold onto their oxygen atoms with a grip that remains stable even as temperatures rise toward 400 degrees Fahrenheit. In this capacity, cobalt acts as a thermal gatekeeper, providing a wider margin of safety for the high energy demands of modern transportation. Beyond the realm of portable electronics, the 77th element serves as the indispensable foundation for the superalloys that power global aviation. Inside a modern high-bypass turbofan engine, the conditions are a literal physical purgatory. The turbine blades, which are responsible for extracting energy from the burning fuel to keep the aircraft aloft, must operate in a stream of gas that reaches temperatures exceeding 2000 degrees Fahrenheit. This temperature is actually higher than the melting point of the individual metals that constitute the blades. Simultaneously, these components spin at over 10,000 revolutions per minute, subjecting the metal to centrifugal forces equivalent to hanging a heavy freight locomotive from the tip of each blade. Under these extreme conditions, most materials suffer from a phenomenon known as creep, a slow, permanent deformation where the metal atoms begin to slide past one another, causing the blade to stretch until it strikes the engine casing, resulting in a catastrophic mid-air failure. Cobalt-based superalloys are the only materials capable of resisting this deformation. To explain the engineering of this on the fingers, a superalloy is like a microscopic jigsaw puzzle where the pieces are locked together with a high-temperature epoxy provided by cobalt. Because cobalt possesses a high melting point and a unique crystal structure that remains stable across a vast thermal range, it prevents the other atoms in the alloy, such as nickel, chromium, and tungsten, from moving out of their assigned positions. It reinforces the grain boundaries of the metal, acting as a molecular glue that refuses to soften. Without the constant work of cobalt atoms holding these turbine blades in their precise aerodynamic shapes, international air travel would be an impossible risk, as the engines would literally melt and pull themselves apart within minutes of takeoff. Cobalt is the material that turned the heat barrier of jet propulsion into a manageable engineering variable. In the field of heavy industry and manufacturing, Cobalt acts as the industrial diamond of the tool world. High-speed steel and cemented carbides, which are used to drill for oil miles beneath the Earth's surface or to carve the engine blocks of automobiles, rely on cobalt as a metallic binder. In a tungsten carbide drill bit, the cobalt does not do the cutting itself. Instead, it forms a tough, ductile matrix that holds the brittle, diamond-hard carbide grains together. This is analogous to a brick wall, where the bricks are indestructible stones and the mortar is a high-strength, flexible metal. The cobalt allows the tool to absorb the violent shocks and vibrations of industrial drilling without shattering, while its thermal resistance ensures that the tool does not lose its bite as it heats up to 1000 degrees Fahrenheit from pure friction. The unique nuclear properties of cobalt also provide a critical service in the field of modern medicine and industrial safety through the isotope cobalt-60. This material does not occur in nature. It is manufactured by placing stable cobalt into a nuclear reactor and bombarding it with neutrons. The resulting cobalt-60 is a powerful emitter of gamma rays, high-energy photons capable of penetrating solid steel. In hospitals, these rays are used in gamma knife surgery to destroy deep-seated brain tumors with sub-millimeter precision, effectively using the energy of nuclear decay as a non-invasive scalpel. In the industrial sector, cobalt-60 is used for non-destructive testing, allowing engineers to see through the thick welds of a nuclear submarine or the structural beams of a bridge to identify microscopic cracks before they lead to a collapse. Cobalt is the element that allows us to see through the solidity of our world, utilizing its high-energy signature to protect both our health and our infrastructure. The cost of this total dependence is an economic and ethical bottleneck that has turned cobalt into the most strategically sensitive metal on the planet. Because the element is so rare and its extraction is so geographically concentrated, the global supply chain is characterized by an extreme degree of fragility. We are currently building a future of green energy and digital connectivity upon a foundation of a material that is difficult to find, difficult to refine, and impossible to replace. Cobalt is the white petroleum of the 21st century, a substance that has moved from the realm of kobold curses to the center of a global industrial race. The hidden engine of cobalt is therefore a story of absolute structural integrity. We use it when we need a material that will not melt, will not bend, will not break, and will not release its oxygen under pressure. It is the metal of the extreme case, providing the stability required for the most volatile processes of our age. We do not see the cobalt in our phones or our jet engines, yet our high-speed, high-resolution, and high-travel reality is entirely dependent on its stubborn refusal to change. It is the material that turned the predatory reputation of the medieval gnome into the guardian role of the modern age, proving that the most unyielding and difficult substances in the Earth's crust are often the ones that allow us to push the boundaries of what is possible. Without the constant, silent work of the 27th element, the machines of the 21st century would literally lose their grip, returning to a state of thermal and mechanical chaos. Cobalt remains our most essential stabilizer, the silver-blue anchor in a world of high-speed energy and fire. The ultimate legacy of the human species upon the planetary record is traditionally conceived in terms of architectural ruins or linguistic archives. Yet the most durable and uncompromising testament to the modern era is a material that occupies a unique intersection between artistic permanence and high-energy physics. While the majority of the materials utilized by contemporary industry are destined to succumb to the relentless pressure of chemical entropy, the 27th element possesses a functional immunity to the standard cycles of decay. Cobalt is the element of the eternal signature, a substance that provides a degree of physical and visual consistency that spans millions of years. Whether it is locked within the crystalline lattice of a sapphire blue glaze on a piece of ancient porcelain, or serving as the structural stabilizer within a discarded lithium-ion battery buried in a landfill. Cobalt does not fade, does not oxidize into dust, and does not lose its identity. This final exploration into the enduring presence of the blue demon reveals a material that will serve as the primary chemical biographer of our civilization, marking the brief moment when a biological species learned to harness the most stable and vibrant forces of the atomic world. The fundamental reason for this extraordinary longevity is the thermodynamic stability of the cobalt-silicate bond. To explain this on the fingers, most pigments used in human history, such as those derived from plants or insects, rely on complex organic molecules that are held together by relatively fragile connections. When these molecules are exposed to the ultraviolet radiation of the sun or the oxygen in the atmosphere, those bonds are systematically dismantled, causing the color to bleach and the material to disintegrate. Cobalt-based pigments, however, operate through a process of mineralogical integration. When cobalt oxide is heated with silica and alumina in a kiln, the cobalt atoms do not merely sit on the surface. They are incorporated into a spinel structure, a rigid three-dimensional geometric cage of oxygen and aluminum atoms. This cage acts as a molecular shield of near absolute efficiency. It protects the cobalt atoms from chemical attack and prevents the corrosive noise of the environment from altering the energy states of its electrons.
This is why a blue tile from the Ishtar Gate of ancient Babylon or a cobalt-decorated vase from the 14th century Ming dynasty appears as vivid today as it did when it first emerged from the fire. Cobalt is the only material that allows the human aesthetic to be etched into the crust of the planet with a degree of permanence that rivals the geology of the Earth itself. In the deep archaeological record of the future, millions of years after the decline of human industrial activity, the 27th element will serve as the definitive stratigraphic marker of the Anthropocene. When the steel skeletons of our megacities have long ago returned to the soil as amorphous streaks of orange iron oxide, and our plastics have been pulverized into microscopic carbon chains, the concentrated nodes of cobalt will remain. Future geologists, whether they are descendants of a renewed human species or observers from another world, will encounter a distinct blue horizon in the sedimentary layers of the Earth. This horizon will not consist of natural mineral veins, but of anomalous high-density concentrations of cobalt, nickel, and lithium. These deposits will represent the technofossils of our digital infrastructure. To explain the engineering of this record on the fingers, in nature, cobalt is a diffuse and rare element, spread thinly across the crust at concentrations of only 25 parts per million. Human industry has acted as a giant planetary funnel, extracting these trace atoms from every continent and concentrating them into trillions of uniform, highly engineered devices. The discarded battery of an electric vehicle or a smartphone is a concentrated mineral vault that does not exist in the natural mineralogy of the Earth. As the polymer casings and copper wiring of these devices eventually dissolve in the groundwater over hundreds of thousands of years, the cobalt oxide cathode materials will remain as stable, insoluble residues. They will settle into the accumulating silt and rock, creating a chemical autograph of a civilization that mastered the art of atomic concentration to power its mobility. Cobalt will tell the story of where we lived, how much energy we consumed, and the precise level of our technological sophistication, with a degree of honesty that no written record can match. The legacy of cobalt also extends into the most intimate of biological records, the history of metabolism. Cobalt occupies a unique position in the biosphere as the only metal that is the central component of a vitamin, specifically vitamin B12 or cobalamin. To understand the biological trace in eternity that cobalt provides, one must analyze the structure of this molecule. At the heart of B12 sits a single cobalt atom, held in a complex ring structure called a Corin ring.
This is the only known instance in all of human biology where a metal is directly bonded to a carbon atom. This cobalt-carbon bond is a masterpiece of molecular engineering. It is stable enough to survive the acidic environment of the stomach, yet flexible enough to facilitate the high-speed transfer of methyl groups required for DNA synthesis and the maintenance of the nervous system. Because B12 is produced exclusively by specialized bacteria and then moves up the food chain, the cobalt atoms in our bodies are part of a biological relay that has functioned for over 2 billion years. Even if the human species were to vanish tomorrow, the cobalt cycle within the microbial world would continue unabated. Every atom of cobalt that currently facilitates a thought in a human brain will eventually return to the soil, where it will be reabsorbed by the nitrogen-fixing bacteria of a future ecosystem. Cobalt is the element that bridges the gap between the inorganic minerals of the crust and the high-stakes complexity of biological life. It is the silent regulator that ensures the blueprints of life can be read and replicated, providing a permanent chemical link between the deep history of the planet and the future of evolution. The ultimate fate of the 27th element on Earth is dictated by the slow, grinding machinery of plate tectonics and the eventual transformation of the solar system. Over the next 100 million years, the cobalt-rich sediments of our ancient landfills and the blue-glazed ruins of our cities will be carried by the movement of the Earth's crust toward the subduction zones. Here, the tectonic plates are forced back down into the mantle, subjecting the star ash of our era to pressures exceeding 1 million pounds per square inch and temperatures over 2,000 degrees Fahrenheit. In this furnace, the cobalt will finally be liberated from its silicate cages and biological rings. The atoms will be returned to their inorganic, molten state, circulating in the slow, heat-driven currents of the Earth's interior for hundreds of millions of years. This is the ultimate reset button for the element, a return to the volcanic home from which it was originally released by human curiosity. The cosmic cycle of cobalt is finally closed when the sun expands into a red giant, approximately 5 billion years from now. As the solar atmosphere reaches out to engulf the Earth, the planet's surface temperature will rise toward 2,000 degrees Fahrenheit, causing the oceans to evaporate and the crust to liquefy. At this threshold, the cobalt atoms will be vaporized into a brilliant atomic gas. To explain this on the fingers, the blue demon that was forged in the apocalyptic fire of a supernova billions of years ago will finally be released from its terrestrial prison. The cobalt atoms will be returned to the interstellar medium, drifting through the vacuum once more as the same stable, heavy particles they were at the beginning of time. Because cobalt is a stable element, those same 27 protons that once stabilized the battery of a 21st century electric car or provided the blue glow for a stained glass window will continue to exist, drifting through the galaxy as part of the raw material for the next generation of stars and planets. In this cosmic perspective, the history of cobalt is a story of a material that has survived the most extreme filters the universe can provide. It survived a supernova, escaped the gravitational trap of the Earth's core, and was eventually extracted from the arsenic-rich shadows of the deep mines to become the guarantor of our energy future. We have used this element as a tool of superstition and a tool of science, relying on its unique ability to stabilize energy and light to build a world of beauty and speed. Yet, the cobalt is entirely indifferent to these human applications. It does not care for the sapphire blue of the vase or the specific energy of the battery. It simply follows the laws of quantum mechanics and crystalline symmetry. It is the material of the absolute baseline, providing a constant reference point in a world of variables. To look at a piece of cobalt blue glass today is to touch the ultimate survivor of the stars. It is a material that has already seen the birth and death of worlds and is guaranteed to see their end. It is the architect of the biological present and the silent recorder of the geological future, a substance that proves that the most powerful forces in the universe are often those that hide in the most humble and difficult of places. Cobalt is the heavy ghost of the periodic table, the silent stabilizer of our high-tech reality, and the most durable monument to the moment when humanity learned to shape the matter of the universe into an invincible armor of energy and light. Every gram of this silver-blue metal is a testament to the fact that our world is built upon a foundation of high-energy physics, a heavy inheritance that connects the apocalyptic fire of the deep past to the cold, stable peace of the infinite future. Cobalt remains the eternal sentry, a shimmering thread of color and power that runs through the entire fabric of reality, proving that in the grand accounting of the cosmos, the most valuable things are those that refuse to be anything other than themselves. Our high-tech civilization is merely a brief resting stop for a material that was born in the heart of a dying giant and is destined to witness the end of time itself, carrying the memory of our existence in the vibration of a single, brilliant blue photon.